Begin the process by importing the raw STL data into the Blender environment using the File Import command. To ensure precise mesh oversight, enable the Statistics overlay to monitor the vertex count throughout the restoration. Next, activate the unit system and edge length display. Since the specimen is microscale, approximately 2.5 inches, maintaining accurate spatial dimensions is vital for anatomical comparison. To facilitate fluid manipulation, set the origin of each individual object to its respective geometry, allowing for efficient rotation during assembly. Throughout this process, avoid scaling the meshes, as any alteration of the scale could compromise the integrity of the original fossil morphology. Manually scrubbing the data to remove small artifacts and non-fossiliferous concretions is inefficient. Therefore, a Python script is utilized for automated data cleaning. By executing a script that targets objects with vertex count below 120, we systematically discard secondary mineral deposits and soil clumps that lack diagnostic value or are too small for viable restoration. The code ensures the interface is in object mode before iterating through the scene, unlinking and removing any mesh that falls below the established vertex threshold. To enhance the visual clarity of the reconstruction, I activated the matte cap material capture shading overlay. This feature replaces the standard viewport lighting with a pre-rendered surface map, which is essential for identifying subtle topographic variations across the fossil surface. By adjusting the color profiles within MatCap, I can high contrast the shadows and highlights, making it easier to differentiate between biological bone textures and inorganic mineral inclusions. Furthermore, I enable the cavity shading feature. In Blender, the cavity shader is a critical diagnostic tool that calculates and accentuates the high curvature areas of a mesh, specifically targeting the valleys and peaks of a geometry. By utilizing both world and screen space cavity methods, the software creates a simulated ambient occlusion effect that darkens deep recesses and brightens sharp ridges. This is particularly vital in digital paleontology for revealing minute details, such as vascular foramina, nerve openings, fine cranial sutures, and the porous internal structures of pneumatic bones that would otherwise remain invisible under flat, default lighting. This heightened definition allows for a more rigorous morphological analysis of the fragmented specimen. To identify the biological identity of the specimen, we must isolate and analyze unique diagnostic osteological features. I have identified a specific fragment that I suspect to be a furcula, characterized by its distinct U-shaped, catapult-like geometry. This element is a critical evolutionary marker. Therefore, my primary objective is to prioritize its anatomical assembly. If the reconstruction confirms the functional presence of this wishbone-like structure, it provides definitive evidence that the specimen belongs to an avian lineage, as the furcula is a hallmark of the avian skeletal system used to facilitate the mechanics of flight. Within this specific cluster, I have identified a series of small, articulated vertebrae with a distinct blunt-ended termination, which I suspect to be the pygostyle. In avian anatomy, the pygostyle is a specialized skeletal element formed by the fusion of the final caudal vertebrae, serving as a critical anchor for the rectrices or tail feathers. The presence of this structure is a highly significant indicator of advanced tail evolution. By identifying this blunted fusion point, I can further corroborate the specimen's classification within the avialan clade and begin defining the posterior limit of the spinal column. I have detected the presence of the pelvic complex, localized in close proximity to the previously identified pygostyle. Its relatively dense and consolidated morphology suggests it has maintained better structural integrity than other fragile elements. I am now initiating a reassembly of this region to confirm the spatial relationship between the synsacrum and the distal caudal vertebrae. Successfully articulating this junction is vital for establishing the specimen's core pelvic architecture and overall posterior alignment. To restore the anatomical integrity of this region, I implemented a mirror modifier to achieve bilateral symmetry and integrated supplementary geometry to compensate for the incomplete or eroded sections of the pelvic structure. I continued the exploration by focusing on elongated and patterned fragments. By observing their repetitive structures, I temporarily clustered and aligned them based on their morphological patterns. During this phase, I identified several fragments resembling avian pedal elements. However, these will be processed in a later stage. Once the primary organization is complete, Any unidentified remnants are hidden from the viewport to maintain a clean workspace. These fragments remain accessible for future analysis, as they may represent teeth or other minute anatomical details. Given that the estimated total length of this bird is approximately 6 centimeters, I initiated a precise measurement phase for the collected long bones. To achieve this, I reconfigured the scene units to centimeters and utilized a dual vertex point system to act as a digital ruler for pinpoint accuracy. Each individual bone was measured to ensure it falls within the proportional limits of a 6-centimeter specimen. In the video, you can observe the recorded lengths for each segment. I am currently cross-referencing these measurements to identify the longest and most diagnostic shapes. This calculation remains preliminary, as a specific ecological niche is yet to be determined. For now, the assembly focuses on the most identifiable skeletal axis, extending from the cervical vertebrae down to the pygostyle. At this stage, I initiated the postural adjustment of the pelvic limbs by implementing the Rigify feature set within Blender. By generating a meta-rig and binding it to the reconstructed mesh, I can manipulate the skeletal kinematics with high precision. This allows for a more rigorous biomechanical analysis, ensuring that the anatomical orientation of the legs is consistent with the locomotor functional morphology of primitive avians. The axial skeleton, spanning from the cervical vertebrae to the dorsal vertebrae, exhibited significant taphonomic displacement and fragmentation. Despite the chaotic arrangement, I identified diagnostic markers. The cervical elements are notably more gracile and diminish in scale, while the dorsal series is characterized by the presence of elongated costal processes, ribs, extending laterally. Although these rib structures are heavily fractured, their bilateral orientation remains a critical indicator for defining the thoracic cavity and the primary midline of the specimen's torso. I reintegrated the fragments previously identified as avian unguals, claws, and isolated the associated elongated elements from the dataset. I then initiated the bilateral assembly of the pelvic limbs, articulating the skeletal chain from the tibiotarsus through the Tarrsometarsus, and terminating at the 3-digit pediphalanges. In this phase, I unhidden the previously sequestered skeletal elements to initiate the reconstruction of the forelimb architecture, the wings. I identified these avian wing components by isolating the manual unguals, the claw-like distal phalanges, and their associated adjacent bones. By tracing the anatomical proximity of these fragments, I can begin to articulate the humerus, ulna, and radius, effectively mapping out the primary structural framework of the specimen's flight apparatus. To maintain analytical clarity, I systematically sequester unidentified skeletal fragments, clustering them into a dedicated peripheral group. This organizational protocol ensures a streamlined workspace, preventing cognitive overload during the assembly of more diagnostic elements. These isolated fragments are preserved for secondary analysis, as they may later prove essential for identifying minute anatomical details or clarifying complex taphonomic relationships once the primary skeletal framework is established. I have commenced the refinement of the pectoral girdle, focusing specifically on the articulation between the furcula and the coracoids. I isolated several planar fragments that, based on their anatomical proximity to the thoracic region, likely represent the coracoid elements. Despite significant material loss and the absence of several key surfaces, I am proceeding with digital reconstruction by aligning their remaining margins to approximate their original morphology. By meticulously cleaning the mesh topology and aligning these elements within the 3D space, I am restoring the structural framework necessary for avian flight mechanics. This process involves ensuring the proper dihedral angle of the furcula and establishing its secure connection to the elongated coracoids. This assembly is essential for maintaining the anatomical integrity of the bird's thoracic region and providing a stable foundation for humeral attachment and a connection to the forelimbs. I have identified several planar fragments that, based on their anatomical position, likely represent the sternum. Despite the significant loss of material and the absence of many key features, I am attempting a digital reconstruction of this element. By carefully aligning the remaining margins, I aim to approximate the original morphology of the breastbone, which is crucial for understanding the specimen's thoracic structure and its potential for flight. I have identified numerous minute, ace-rose fragments exhibiting morphological characteristics consistent with dentition. These tooth-like elements were meticulously isolated and repositioned within the rostral, beak, region. In the context of early avian evolution, the presence of these individual teeth is a significant primitive trait, and their integration into the cranial assembly is vital for accurately reconstructing the specimen's feeding apparatus and taxonomic profile. Upon achieving a satisfactory level of anatomical alignment, I proceeded to integrate the reconstructed elements into a unified skeletal model. This final synthesis involves merging the disparate clusters of cervical, dorsal, and appendicular bones into a singular, cohesive framework, effectively restoring the primary structural orientation of the specimen for further morphometric analysis. To address the missing anatomical regions, I utilized Blender to digitally model the absent structures, subsequently integrating them into the assembly. Each synthetic element was meticulously sculpted and positioned to align with the biological morphology of the existing bone fragments, ensuring a cohesive and anatomically plausible skeletal restoration. This concludes the digital reconstruction of the specimen. The blue-coated elements represent the original fossilized material recovered from the scan, while the red-coated elements denote the synthetic restorations modeled to complete the skeletal framework. Given the diminutive scale of the organism and the inherent fragility of avian osteology, many structures were susceptible to taphonomic degradation or loss. This color-coded visualization provides a clear distinction between preserved biological data and the necessary anatomical inferences required to present a comprehensive and cohesive 3D model. Presented here is a comparative visualization between completed skeletal assembly and the original fossilized matrix. The magenta-coated elements represent the primary, unrefined data in its post-taphonomic state, shattered and disorganized as initially found. This side-by-side contrast highlights the extensive digital restoration process, illustrating the transition from a fragmented mineral mass to a structured, anatomically coherent avian framework.